Smartphones connect nearly everywhere to the internet. What if we could use all their towers to connect our sensors and other gadgets to the internet? Would LoRaWAN or Sigfox be obsolete? If you are brave, you will follow my journey and learn a lot about cellular IoT technology and how to survive the minefield it is built on. Then you can decide what to do with LoRaWAN. Grüezi YouTubers, here is the guy with the Swiss accent, with a new episode and fresh ideas around sensors and microcontrollers. Remember, if you subscribe, you will always sit in the first row. Many years ago, we had cheap modules to connect via 2G networks. They were okay, but unfortunately, these networks disappeared over time and were replaced by 4 and 5G networks. New modules for these networks were extremely capable, but expensive and power-hungry. Only recently has this changed, and everybody talks about the new modes like CAT-M1 or narrowband IoT. These modes are made for low-power, low-capacity sensor boards. Exactly what we need, right? Let's check out. Other than with LoRaWAN or Sigfox, we have to look at many things to get it running. The cellular protocols and their low-power modes, the frequency bands they use, the available modules and Arduino libraries, the SIM cards and the roaming contracts, the transmission protocols, the future. Finally, we will be able to compare it with LoRaWAN. Let's start with the low-level protocols. Here we have 2.5 contenders. 2 will be covered and the half only will be mentioned at the end. These protocols belong to the 3GPP standardized technologies and operate on most 4 and 5G networks. The 2 modes are CAT-M, also called CAT-M1 or LTE-M, and narrowband IoT. To understand the technicalities, let's look at the spectrum. LTE, like most modern transmission protocols, uses OFDM with multiple parallel subcarriers and slots. Its basic unit is a physical resource block with a 180 kHz bandwidth, containing 12 subcarriers. 25 such PRBs combine to form a 5 MHz LTE signal. But wait! 25 times 180 kHz is only 4.5 MHz. Where is the missing 500 kHz? It is not missing. It is used to separate channels and it is called the guard band. Narrowband IoT uses 1 such PRB and CAT-1M 6 of them. So you see the first difference. Bandwidth, which usually translates into channel capacity. Another difference comes from ingenuity or greed. Either the MBAs wanted to make money with a useless guard band, or clever engineers offered them this solution. Nevertheless, narrowband IoT can either be implemented in the guard band to generate additional profit, or inside the regular band. CAT-M1 always uses valuable LTE bandwidth. CAT-M1 offers 1 megabit per second uplink and 1 megabit per second downlink capacity. Much more than LoRaWAN, even on SF7. But we will see a lot of it is used for overhead. Narrowband IoT offers a 66 kilobit per second uplink and a 26 kilobit per second downlink. There is also a lot of overhead here. Still, it is plenty for typical sensors. CAT-M started in the US and narrowband IoT in Europe. That is not a coincidence if you ask me. Everything in the US is a bit bigger than in Europe. I am already looking forward to the big engines and the big stakes during my next US stay. Do not complain, I'm a poor old man raised in a different time. Anyway, I digress. As with all communication protocols also made for battery-operated gear, they have to offer power-saving modes. So let's look into what happens when you switch your cellular IoT module on. But before we cover this topic, we have to examine the frequencies used by these modules. Most of the current modules are made for the global market and, therefore, support all these frequency bands. Let's consolidate because some are the same. Still, 10 bands are left. They all are numbered. Unfortunately, they use a cryptic numbering similar to the imperial system. I will never understand. It seems the bands were numbered historically. First came the bands around 2 GHz. Then the sub-gigahertz bands, also called digital dividends, that became available when UHF TV went cable. And finally, the higher bands around 2.5 GHz. Because IoT protocols are made for long range and deep penetration in houses or basements, they typically use the sub-gigahertz bands, like where I live, band B20. This also explains why I said in my last video about LoRaWAN gateways, you need filters for your gateways if you mount them in the vicinity of cellular towers. 868 or 915 MHz are pretty close to the sub-gigahertz cellular frequencies. Now we can continue with looking at the protocol and finally power saving. When we power up our module, it starts to consume a lot of energy. First, it boots up and, if you do not restrict it, starts to scan all bands to find an appropriate signal. Then it detects and chooses the cell. It connects to the cell covered by your contract stored on the SIM card, not to the one with the best signal. Next, it updates its tracking area and registers to the cell. Only now it can start to deliver its messages. As promised, a lot of overhead not needed by LoRaWAN. There, most of these parameters are known in advance. But it has the advantage that at least CAT-M1 supports an organized handover between towers for mobile devices, as we know from our smartphones. Narrowband IoT does not support cell handover. It sticks with the current cell as long as it is reachable. Only then it searches for a new one. So definitively, CAT-M1 has an advantage for mobile devices. Now we have to distinguish between downlink heavy and uplink heavy applications. Let's start with downlink heavy, even if this is not the typical case for sensors. It is a bit easier to explain. After registration, if there is nothing to transmit, the modem goes into paging mode, where it waits for a downlink message. All LTE modems sleep for a very short time during this cycle. If you want more, you can ask the cell for eDRX. If granted, the receiver is switched off for longer periods. The module still consumes milliamperes during this phase. But from time to time, it can receive a downlink message. Of course, with this delay. The carrier decides on the maximum allowed eDRX time. It can be up to 44 minutes for CAT-M1 and up to 3 hours for narrowband IoT. However, as we will later see, there are better possibilities than long eDRX times. This is the first method of saving energy and, as said, mainly for downlink heavy connections. The next phase is suspend mode, where we more or less power the LTE module down. This mode is called PSM and its maximum time is also determined by the carrier. If we exceed this time, the connection is lost and our chip has to re-register to the cell. If we wake up before this time, most of the overhead is not needed because our modem is still known to the cell. This is the preferred mode for sensors that do not need a lot of downlink traffic. If your provider allows, you can even request release assistant indication to shorten the receiving phase further. You see, we have many possibilities. Unfortunately, they depend on the network operator and the SIM card you use. Now we know how the low-level protocols work, and we can go on with the available modules. Most modules on AliExpress are from Simcom. I started with a SIM 7080 mounted on an ESP32 S3 board from LilyGo. You get modules from other manufacturers like Nordic, Kectel, Qualcomm or Sequence. LilyGo also provides some example code that uses the tiny GSM library. However, as its name implies, it comes from the old GSM times, and we have to add code to be fit for the new IoT modes. This is why I use Walter, a similar board with an LTE chip from Sequence. It is made by a small Belgian company and currently is on crowd supply. They started a new open source library that is up to the task, and maybe it will become the new standard for modern protocols. You heard me talking a few times about SIM cards. For our smartphone, you get them from our network provider as part of the contract. This is why I inserted one in my LilyGo board and tried to connect. It only connected using CAT-M1. I tried to get information about IoT SIM cards from all providers in Switzerland, without success. Fortunately, Walter contains a SIM card from Soracom in the UK. Because the SIM card also supports roaming in Switzerland, my sketch worked with it inserted without problems on both protocols. Strange. Later on, I met Harald from Kraut, a German company specialized in such cards. He explained that it is very difficult to create SIM cards for CAT-M or even more narrowband IoT, because these protocols are usually not covered by standard roaming contracts between carriers. So pay attention to the evaluation of the SIM card. I searched for a very long time to find a non-existent error in my sketch. In the end, I contacted my Swiss SIM card provider and they were astonished that their SIM card supported CAT-M1. They thought it did not support any IoT standard. I leave a link to the 2 SIM card suppliers that sell working ones. However, check the availability in the countries you want to use your devices. A trick for the US. It might be easier to use a foreign SIM card because some carriers will ask you for an FCC certification of your device before you can connect to their network using US SIM cards. Not so if your device is roaming. Before we continue with the transmission protocols, we want to see how our device works. For that, we used Walter's sensor example. Because for our sensors we are interested in power consumption, I powered it with a PPK2 power monitor. Here you see what we learned before. The ESP32 switch is on and the modem connects to the network. As soon as the board is connected, it transmits a value and goes to deep sleep. The modem transmits the value via CAT-M1 or narrowband IoT and, after paging, goes to sleep too. After 1 minute, the ESP32 wakes up and transmits the next value. To see what happens inside the cellular network, I was lucky that we have an RF lab in Switzerland, where they have this base station simulator from Anritsu. Like that we can see how the transmission works also in the cell tower. After powering up, our device requests for a registration. You see, a lot of information has to be exchanged during this process to authenticate your device. You also see that this is a bidirectional communication, and our device knows if it is connected and data can be transmitted. This explains why it took so long. Watch also the power consumption during this phase. It is quite high. After registration, data transfer is fast. Also because Walter's library uses an optimized protocol. After the paging phase, where the module waits for downlink traffic, it goes to sleep too, and the current draw is only microamperes. If we wake up before the maximum PSM time, our device stays known to the network and no registration is needed. The power consumption is 30 to 50% less and probably could be optimized further by using RAI. Keep in mind that these networks increase the output power and the repetition rate when the quality of the connection is low. Here in the basement, the same transmission takes longer, and if you do not pay attention, it can deplete your battery very fast. A big difference compared to LoRaWAN. So we know how the communication with the tower works, and we can continue with the transmission protocols. Modern modem chips support IP and MQTT. Coming from IoT, I prefer MQTT of course. It worked fine with the SIM 7080, even with the encrypted MQTT-S protocol. Unfortunately, this protocol is not optimized for cellular. That is why the specialists prefer UDP and CoAP to transfer messages. This was the main reason I used the Volta board for my tests. As said before, I distinguish between sensor and actuator boards. In reality, I could also distinguish between battery and mains-powered boards. For mains-powered devices, most of the power optimization discussed before are not very important. If connected to mains, you do not need to sleep and you could use the MQTT protocol. Just keep in mind that these modules have to dissipate the power, and maybe it is important to save power to avoid overheating in tight spaces. So for mains-powered devices or for devices only used for a short period, the tiny GSM library and such a LilyGo board are perfectly fine. We have now covered the major aspect of IoT via cellular networks and are ready to compare it with LoRaWAN to answer the question of the clickbaity thumbnail. Here are the differences that matter to me. Moving versus stationary devices. The millions of cell towers neatly distributed across the globe offer incredibly high coverage. LoRaWAN, even with a helium network, has only a fraction of this coverage. So, if you have moving devices, cellular has a huge advantage. If your devices are deployed in a defined area or in an area without 4G coverage, they can be covered by a LoRaWAN gateway at low cost. Also indoors and in basements where 4G coverage is weak or non-existent. ALOA versus bidirectional communication. LoRa uses the ALOA protocol without confirmation, so the sender does not know if the message arrived. This is okay for non-time critical data, but you probably would not want to transfer money across such a connection. Throughput. LoRa and LoRaWAN are exceptionally slow protocols, hampered by the usage of non-licensed band with a 1% duty cycle. Narrowband IoT and, even more, CAT-M1 have much higher data rates and no duty cycle limitations. So they are the right choice if you need higher data rates. Complexity. LoRaWAN is a simple technology compared with cellular. Writing programs is quite easy and straightforward. Deploying gateways allows you to control the overall infrastructure if you want. Cellular, on the other hand, is complex because it is a jack of all trades, and many companies are involved. In addition, because IoT SIM cards are dirt cheap, only large contracts are interesting for the providers. If you are small, do not expect too much. So ask a specialist for help if you deploy your first project. Price. LoRa modules are still cheaper than cellular modems. However, the price difference gets smaller, particularly with specialized chips that only support narrowband IoT. Deploying a LoRaWAN gateway is a fixed cost, whereas SIM cards cost an annual fee of a few dollars. Writing and testing code for cellular devices will be more expensive until the complexity becomes smaller and more know-how is in the markets. Power consumption. After all my tests, I did not find a big difference in power consumption between CAT-M1 and narrowband IoT. However, Both cellular IoT protocols in an uplink-only scenario consumed considerably more energy than LoRaWAN, particularly with weak signals. This has to be expected because of the two-way nature of the communication. So, in this area, I expect LoRaWAN to be the winner for a long time to come. Some fanboys state 10 years of battery lifetime for cellular sensors. If you read the fine prints, they suggest a once-per-day upload of consolidated sensor values. I assume to prevent the big power drain of the connection process. Future. LoRaWAN has not evolved rapidly over the last few years. Cellular, on the other hand, evolves quickly and in big steps, so expect changes here. Fortunately, narrowband IoT and CAT-M1 are part of the 5G specifications. But new protocols are coming. Together, they are called 5G RedCap. I hope this video was able to show that both technologies have advantages and disadvantages, and so help you make the right decisions. One last thing. In the beginning, I said that we have 2.5 protocols to choose from. So far, I have only covered narrowband IoT and CAT-M1. The third IoT protocol is CAT-1 bis. Its throughput is higher and its range is smaller. However, because it is covered in the standard roaming contracts, its handling is easier. Unfortunately, typical IoT modules like the SIM 7080 do not support it. This is why I only counted it half. That was all for today. As always, you find all the relevant links in the description. I hope this video was useful or at least interesting for you. If true, please consider supporting the channel to secure its future existence. Thank you. Bye.